Question 6 was the cyclohexane question. And a very specific problem happens when we have substituents on adjacent carbons in a cyclohexane ring. That's what part B of the question is getting at. Actually, part A as well. So, first, the axial positions on adjacent carbons point in opposite directions. So that's going to be trans, one up, one down. So I can just go ahead and draw that as one of my two conformations, one of my two chairs. That's trans. They're both axial here, which means after I ring flip that, they're both equatorial. Now this is where we start to run into some trouble here. Okay, so these are both equatorial carbons. So in the first case, I have diaxial interactions here on the top face. I have another set of them on the bottom face of the ring. So I have a large number of diaxial interactions here that are significant and severe. In the other case, well, now I don't have diaxial interactions because I have no axial substituents other than hydrogens. But now I have these two, and they're gauche to each other. So those two chlorines are going to be problematic for me, that they are interacting with each other. So if I'm looking in a way where I can see those in a Newman projection, I'm going to take this as my front atom for one of them. If I do that, what I get is this, where I have the ring drawn like this. The front atom has an axial chlorine here, an equatorial chlorine here. The rear one has the other equatorial chlorine. And everything else around my Newman projection is a hydrogen. Well, this is a gauche-butane interaction. And that's the problem, is that by getting away from the diaxial interactions where they're interacting with the ring, I've actually forced them into a conformation where they're interacting with each other. So it's not ideal. If I had the cis 1,2-dichlorocyclohexane, they're always in interaction with each other because one of them is always axial, one of them is always equatorial, so one would always be interacting with the other. In this case, the gauche-butane interaction can be escaped, but by doing so, we end up with massive diaxial interactions. So for smaller groups, that might be okay. Chlorines are fairly large, so neither of these is ideal, but the diaxial interaction is generally worse because it comes in pairs. So I've got basically 4 negative interactions between a carbon and a chlorine, 2 sets of pairs of diaxial interactions for the first conformation I drew. For the second one, I have only 1 negative interaction, but it's between 2 fairly large chlorines. So neither of these is great, but more likely, of course, is this one's going to be my stable one. I didn't ask you to tell me which one was more stable, but that's why.